So where were we? A few hours ago, we were trying to prove this result. We nearly got through it, so we'll finish it off. So just to really quickly recall, we're dealing with a P group G. So every element in G has an order power of a prime. From an earlier result, we know the order of G itself, meaning the count of the number of elements that it has, is itself an order of a prime, order of that same prime, P. So the prime involved is P here. And what we're proving here is that it's possible to split off from G to express G as a direct product, an internal direct product, but isomorphically that's the same as an external direct product. But it's possible to express G as being isomorphic to the direct product of a cyclic group generated by one of its elements. So it's an element from the P group. So this element, little g, has order power of a prime. So this is a cyclic group whose order is a power of the prime P. And direct product with another group, with a subgroup of G. Okay? And by induction, that will mean that you can, if we can always do this for any finite billion P groups, then we can keep doing it, because the subgroup H that's left here, because it's a subgroup of G, it itself consists of elements whose order is always a power of P. So it itself is a P group. So you can apply the lemma to H. So you can split off a cyclic bit off H. And then whatever's left behind, you can split a cyclic bit off that. So you can keep going until you have your original P group G expressed as a direct product of cyclic groups. All of the cyclic groups have order, a power of that same prime P. Okay? So using induction, you can get that long direct product. So really what you have to prove is just you're able to split off one of the cyclic P groups of G and express G as a direct product. So by the earlier result, G is a P group. So we know the size of G is power of its prime. Okay, I'm not going to talk to the whole thing again, but I'll just zip through it to bring us back up to where we are. So we know the order of G is P to the n, so we're going to prove it by induction on that experiment there. To the base case is kind of true automatically. Then we single out, okay, so this element little g is special. It's got maximal order in the group G. So G, we select an element little g of maximal order. We named that order as P to the n. We then, okay, it could be, this is our first little note at the side, it could be that this is all of G, that G is just a straight cyclic group, single cyclic group. In which case, the result is just automatically true. Just take H to be the trivial subgroup. And so G is effectively equal to that. So there isn't really any splitting off to do. G is just one of these cyclic groups. If that's not the case, though, then this cyclic subgroup generated by little g is not all of G. So there are some other elements in G that are not in here. And then you let little h be one of those with minimal order. Minimal order this time. Okay. Minimal order of all the elements that are not in cyclic subgroup generated by G. And it's this. Okay, this element little h generates a cyclic subgroup called capital H. Just the cyclic subgroup generated by that. And this is the curious thing, yeah, I think maybe a slightly poor choice of notation that it isn't this subgroup H that's exactly this one H that's going to appear in the statement result, but it's one that grows out of it. We may have to slightly enlarge that H to get the subgroup that works here. I think if I was rewriting it myself, I'd choose a slightly different letter for that. But anyway. So in order to set up the conditions for a direct product, we have to show that this thing has, not that it's completely disjoint from cyclic subgroup generated by G, but as disjoint as it can be, but they only overlap in the identity element. Remember, every subgroup contains the identity element. So two subgroups will always have some overlap, at least the identity element. But here we're saying that there's nothing else. It turns out that in order to do that, we prove that the element that the subgroup capital H has order P. In other words, the order of the element little h was P. Okay. We explained on a explanatory paragraph why that was sufficient. I won't go through the proof of it again. We achieved that. We concluded that the order of H was P. So the order of this element little h is P. So that's good. H has got, and this kind of more or less brings us up to speed here. The subgroup H has got P things in it. Okay. The size of G is a power of P. Okay. We're in an abelian group. All subgroups are normal. So you take any subgroup, you can form the factor. How many elements does the factor group have? And this is a case where this fraction type notation for the factor group, although it's not fraction G divided by H, but it is a very good notation where it's not confusing in that the number of things here is the number of things in G divided by the number of things in H. Remember, the number of elements here is the number of cosets of subgroup H in G. The number of cosets is the size of the big group divided by the order of the group. That gives you the number of different cosets in the partition G. So we understand very well the number of things in G. It's P to the n minus 1. Because it was P to the n things in G itself. You divide it out by H. H we know has size P. So the size of the factor group G naught H is P to the n minus 1. So we know that exactly. Now we're investigating, for purposes that will become clear, we're asking ourselves, what is the order of this coset? This is the coset associated to this element little g of G, which has maximal order in the group, the original group G. What is its order in the factor group? Then we had a side, so this is bringing us back up to speed. We had a side consideration in our further explanatory paragraph here. How does the order of something in a factor group relate to the order of the representative? It's, well, factor groups are homomorphic images of the original group. In any homomorphic image of an original group, the order of the image of an element always divides the order that the element had back in the original group. Okay. This fits into this picture that factor groups, homomorphic images of groups, are simplified views of G. In the special case where the homomorphism is an isomorphism, it's not a simplified view of it. It's an exactly replicates the group structure of the original. Maybe in a different mathematical setting, you may have transferred the objects into different kinds of mathematical objects, but whatever groupiness about the image here is exactly the same as the original one when it's a one-to-one and onto homomorphism, when it's an isomorphism. But in general, for homomorphisms that are not injective, that do collapse down different elements on top of each other, but the homomorphic image is a simplified view. And this is one aspect of that the order of the image of an element must divide the order that the original element had. Having a high order, an element having a high order is kind of complex behavior, if you like. The group generated by that element is large if it has a high order. When you apply a homomorphism to it, you maybe simplify it. The best you can do is to keep the order the same. But probably if it's a non-injective homomorphism, it can reduce the order of X down to a divisor, a factor of the order that it had to begin with. N here was the order of X. So that's the idea of the homomorphic image being a simplified view of G. The element X, which maybe had a complex nature, generated a large cyclic subgroup. Its homomorphic image will generate a smaller one. So it's a simplifying behavior. So we need to understand that. So then this question then is, this special element of the factor group, the coset generated by this element little g of maximal order in G, we know the order of little g is p to the m, that was named at the start. So what is the order of coset gh in the factor group gh? By our little explanatory paragraph there, the order that GH has must divide the order of G. So the order GH, it must divide by the power of P, so it must be a possibly smaller power of P. Maybe the full P to the M, but maybe less than. Can't be anything else. Must be just some other power of that same prime P. So we investigate that. But the claim is that it's the same. So the claim is that we will show the order of GH and the factor group G mod H be the same as the order of G. So this is a little proof by contradiction here. Yeah, proof by contradiction. If it's the case that it has strictly less order, strictly less than P to the M, well, that means it has order P to the K for some K strictly less than M. So that means it'll have order P to the K where K is less than or equal to P to the M minus 1. So this if statement here is equivalent to the order of GH being P to the K where K is less than or equal to M minus 1. That's the equivalent to this statement here. Okay. We know its order must divide the order G had, so the order of this must be some power of P, but if it's strictly less than the order that G had, means it can't be order P to the K, so it must be P to the M, so it must be P to the K for some K less or equal to M minus 1. So in other words, when you raise it to the power P to the M minus 1, what that is there, superscript's a little bit distinct. When you raise it to the power P to the M minus 1, that means you're raising it to a power which is some multiple of its order. It might be exactly its order. Maybe its order is P to the M minus 1. But if K is even smaller, then P to the M minus 1 is a multiple of its order. And when you raise an element to a multiple of its order, that means it's going to be equal to the identity. Because you're raising it to a certain power that brings it back to the identity, and maybe a multiple of that. So you're always arriving back at the identity. So the power of this element GH must be the identity. Now, what's the identity? Which coset in this factor group is the identity? It's the coset H itself, or in other words, E times H, which is just the same as H. So this element raised to the power P to the M minus 1 must be equal to the identity in the factor group, which is H. Now, a rule for multiplying cosets is when you multiply cosets, it's the same as multiplying the representatives. When you raise a coset to a power, it's the same as the coset corresponding to the representative raised to that power. But by definition of coset multiplication, this power is the coset corresponding to G to the power of P to the M minus 1. Therefore, if the coset H is equal to this element times H, that means this element must be in H. Because the only time you have a coset corresponding to an element multiplied by H being equal to H itself is when the element you chose was in the subgroup, in H to begin with. So this equation here implies that G to the P to the M minus 1 is in H. But G to the P to the M minus 1, being a power of G, is certainly in the cyclic subgroup generated by G. Yeah, so it's a power of G. That's exactly what the cyclic subgroup generated by G is, all those powers. So it's in H and it's in this. Therefore, it's in the intersection. But that's why we went to the trouble of dealing with the intersection before. But we've already established the intersection only consists of the identity. So that means if this element is in the intersection, it has to be equal to the identity. So it must be in the intersection, which is equal to the identity. So in other words, that implies G to the P to the M minus 1 equals the identity. But that contradicts the fact that the order of G is P to the N. That's the smallest number, such that when you raise G to that power, you get the identity. But here is a clearly smaller one, P to the N minus 1, which gives you the identity. So that can't be true. Because otherwise the order would be at most P to the N minus 1. but we already named the order as p to the n. So that's a contradiction. Where did that come from? That contradiction is you reel back until you find an assumption that led to that contradiction. It was this assumption here. If the order is smaller than, if the order of GH is smaller than the order GN. So you know it can't be smaller. Therefore it must be equal to. Because just generally, because it's a homomorphic image, the order, the coset GH divides the order of G. That's what you get from it being a homomorphic image. So the order can't be less, therefore it must be equal to. So the order of GH is p to the m. But remember, p to the m, this element little g was very, very special. It had maximal order in G. So here we have an element, a coset, GH, in the factor group, which has order p to the m. But that has to be a maximal order in the factor group here. Okay? Because remember, NB, every element XH in the factor group G mod H has order less than or equal to the order of X, the order of X in G. Actually, even stronger than that, its order must divide the order. Even stronger, but at least less than or equal to. So if p to the m is the maximum order you can find in elements of the original group G, and here we have a coset which itself also has order p to the m, therefore this must have maximal order in the coset. Okay. But the size of the coset, remember, size of the coset is, sorry, I've kind of got extra notes all over the place. NB, the size of the factor group is the size of G divided by the size of H. So that's p to the n minus 1. P to the n was the size of G. H is size P. Size of the factor group is p to the n minus 1. That means it's covered by, because remember, we're in the middle of an induction proof here. Reel it back. Where did he say? Assume the lemma holds for all integers k. Now these are exponents on the size of p. Exponents on p for the size of G. So it holds for all exponents strictly less than n. Well, here's a group, the factor group. Remember that assumption was over all groups, all finite abelian groups. So G was a finite abelian group, its factor group was a finite abelian group. It's got size less than p to the n. So it's covered by the inductive hypothesis. So therefore, from the factor group, we can split off. So here we are, we're now applying the lemma. See, he says, so by the correspondence theorem and our induction hypothesis, so applying the lemma, applying the result of the lemma to the factor group, we know the factor group is isomorphic to the cyclic subgroup generated by that element of maximal order, which is this coset GH. I should probably say before this, it's GH isomorphic to this thing cross, I want a letter related to K. Let's say a curly K. Just a handwriting script K. This K is a subgroup. K is a subgroup of the factor group G mod H. That's what the result says. You can split off the cyclic subgroup generated by the element of maximal order, direct product with a subgroup of G. So here we can split off the cyclic subgroup generated by this element of maximal order with a subgroup curly K of G mod H. Now, okay, he also says the correspondence theorem. What was the correspondence theorem? Correspondence theorem was theorem 11.13. So the correspondence theorem correspondence theorem 1113 said subgroups of a factor group exactly correspond to subgroups of the original group that contained the subgroup that you quotiented out by, that you factored out by. So I won't flip back in the pages to it, but it said that subgroups of the factor group exactly correspond to subgroups of the original group G, which contained the subgroup that you're doing the factoring out by. So this subgroup curly K of the factor group corresponds exactly to a subgroup K of the original group G. So this sentence is continued at the top of the original page. He says what this K is. K is a subgroup of G containing H. So this where K, which contains H, is a subgroup of G. Subgroup of G containing H. So if it's a subgroup of G containing H, the correspondence theorem tells you that this subgroup curl of K is exactly K mod H. So that comes from the correspondence theorem. So that first green line comes from applying the induction hypothesis. The next one comes from applying the correspondence theorem. Okay, so turn the page. See there, he says for some subgroup K of G containing H. Remember I said that it was maybe a slightly unfortunate choice of letter H, because this H that he finds in the middle of this proof here isn't quite the H in the statement of the theorem. The subgroup H that we're proving the existence of is this subgroup K. Okay, so we know that it exists. So we want to show, so the very final bit is to show that in fact G is the direct product of that cyclic subgroup little g with K. To prove you've got an internal direct product, you have to show that the intersection of the two subgroups is minimal, that it's just equal to the identity element. Well, that's true because if you did have a B, say, in the intersection of these two, then little bh would certainly be in this one here, the cyclic subgroup generated by the coset GH, and it would also be in the factor group K mod H, okay, because B was in K, so this subset, this coset BH would be one of the things in the factor group K mod H. But if B was in cyclic subgroup generated by G, then BH would be in the cyclic subgroup generated by these two. Came from applying the result of this lemma we're proving, implying the inductive hypothesis to the factor group. So this is an internal direct product. So the intersection of these two is just the identity. Okay. So in other words, this coset, because the intersection of these two is just the identity, and that H there is the identity in the factor group G mod H, coset H. So BH must be equal to H. That's the consequence of that, is that BH must be equal to H. Well, when is a coset BH equal to H? It must be that B is in H. If you take an element outside of the subgroup, then you get a different coset to the subgroup itself. So if BH is equal to H, it must be that B is in H. But if B is in H, then it's already started out in cyclic subgroup generated by G. So if it's now in H, if it's now additionally in H, then it's in the intersection of cyclic subgroup generated by G and H. But a couple of paragraphs ago, we proved that that only consisted of the identity. So therefore, from this line here, you get B is equal to E. So anything in the intersection of cyclic subgroup generated by G to K has to be the identity. So that proves that the intersection only consists of the identity. So we got these two elements, we got these two subgroups, cyclic subgroup generated by G, this new subgroup K, they have trivial intersection. And this last bit is what my last explanation paragraph is going to be for. He claims then that it follows that G is equal to the product. See, this is the last thing you need for an internal direct product. You need the two subgroups, cyclic subgroup generated by G and K. They must have trivial intersection, and their product must be all of G. Now, he just says it follows that works, but I think we need a little bit of a claim here. So this is just at the end of the proof. This claim that G is equal to cyclic subgroup generated by G times K. I think we need a little proof by this. Once we do know that, that implies that you've got the final result. That your group G is the internal direct product of cyclic subgroup generated by little g. Okay. But this final thing, I think, needs a little bit of proof. Okay. So let X be any element of G. Normally you'd say little g, but little g is a special role. It's a special purpose of this proof. So I'm just going to let X be any element from G. Okay, we have to show, in order to prove that G can be written as this product here, we have to show the existence of an R and a little k such that X is equal to G to the R times K. Because then X will be in the product of these two. Yeah, something in the cyclic subgroup generated by G times a little k. Sorry, little k is in where this little k is in the subgroup K. Okay, how are we going to do that? Well, we have to pass to the factor group first. The factor group XH. Okay, so we know XH, the coset XH, that's an element of the factor group G mod H. We know the theorem is true in that. So we know that this is, so let's say we know that this is an element of the product of the cyclic subgroup generated by the coset GH and the subgroup K mod H. So therefore, our coset XH is equal to something from the cyclic subgroup generated by GH. So that will look like something, that'll look like a coset generated by G to the R for some R. And what do you look like when you're in here? When you look like something, you look like some K times H. So that's true for some R, some integer R, and some element little k in K. I'm kind of falling victim to the same trick. This K won't necessarily quite be this K we're looking for here. Maybe multiplied by something H. We'll do that in a moment. So this coset here is equal to this coset. Now, one of the things that's in this coset on the left is X itself. Remember, H is a subgroup. It contains the identity element, E. So one of the things in this set here, remember this is a coset, is X times E, namely X itself. So that means X, the element X, must be one of the things in here. And one of the things in here will be a G to the R times a H1 times a K times a H2. And that's for some little H1, little H2 in H. Okay, but that triple product there, H1K, H2, that's actually an element of K. Remember, H is a subgroup of K. When this K popped into being, it popped into being by applying from applying the inductive hypothesis to the factor group G mod H, but this was some subgroup K of G containing H. So H is a subgroup of K. So this triple product here is something from H times something from K times something from H. It's certainly an element of K, because it's 3 elements from K multiplied together. So that's certainly equal to, let's call it a K1. There's some K1 in K. So you can indeed write any element X from the group as some power of G to the R for some R, times some element from K. So therefore, that implies that G is equal to the product of those two. Okay, and so that's what we need for the internal direct product. That's what we need for the internal direct product. We've got two subgroups, cyclic subgroup generated by G, the subgroup K. They've got trivial intersection. And any element from G can be written as a product of elements in these two. So as a set, G is equal to the product of these two sets. That's what you need for the G as the internal direct product. So G is isomorphic to the direct product of those two. So now, finally, we can put together the proof of theorem after 2 point. And we'll finish on that today. So, first of all, any questions? No. Okay. So together with that proof there in the book, together with those extra explanatory paragraphs, I think, let me just put a red as I have been doing, just when we look at the notes afterwards. So that red explanatory paragraph there was explaining this claim here, this claim that G is equal to the product of those subsets. So this is really, you see, he just says now that you can put all this together. Yeah. So putting these lemmas together, proves a fundamental theorem of finitely abelian groups, the fundamental theorem of finitely abelian groups, the FTFAG, so to speak. It's worth just outlining the key steps. So lemma 13.8. So first of all, G is any finite abelian group. The order of G is n, and n is a power of R. N has got a prime factorization, product of powers of primes, PIs. Lemma 13.8 says that G is isomorphic to G1, the direct product of G1 by G2, by all the way up as far as, now this one goes to GR. You got one of these for each of these primes, where GI is the PI primary component of G. Namely, GI consists as a set of every element from the group G, such that the order of X is some power PI to the Y, say, of that prime PI. What we aren't saying is that every element in G has power, has order, power of one of these primes. We're not saying that. We're not saying that G is the union of these, but that you can isolate special elements. The special elements in G, which all have order some power of P1, gather them all together in G1. The special elements in G that all have power, that all have order some power of P2, special elements. You gather together all these special elements, and when you take the direct product of them all, you get everything in G. So a typical element of G is not in any one of these individual groups. A typical element of G is expressible as a product of elements, one from each of these groups. Yeah. So your average typical element in G will have order, which is some divisor of n, which will typically be some mixture of these primes to lower orders. Okay. The PI primary component consists of all those special elements which are who have order some power of that particular prime. So that's lemma 13.8, and then lemma 13.9, the one we just proved, tells you that each of these GIs, these ones, is isomorphic to a direct product of cyclic groups. So a bunch of these cyclic groups Z. Now there are indexes to put here. The index here is always some power of, because they're these direct summands of their cyclic subgroups of the PI primary component. So these are all cyclic subgroups whose order is some power of PI. So I have to put in superscripts there. So let's say this is B1 or a beta 1, beta 2, and this goes up as far as some size, beta whatever, beta. I just don't want to use a letter I've already used. Let's say a tip, and it also has to have a subscript I. So this will be some upper limit I, if you like. Okay. So just don't worry about how many there were. Just understand the lemma 13.9 says, and of course, well, you have to use it with induction, because the lemma just tells you how to split off one cyclic subgroup and the direct product with another subgroup, but then that other subgroup is smaller. So by induction, you can split off something else off that. So each of the PI primary components is a direct product of things like these. So then when you replace each of these with its expression as a direct product of cyclic groups, do that for each of these, what you'll be looking at is the big direct product of cyclic groups. Okay. So putting all these together, gives the required direct product for G. So it was a bit of an effort to get there. We had to go through a number of, preliminary results. But it is really nice, I think, to see something as powerful as that come together. And it's not something you can just sit down and prove in one little paragraph. It does, and it does draw together almost all of the bits of the theory that we've done up to now. And it also relies on a lot of the number theory that we did. Things like the prime factorizations of numbers and properties of divisibility, and so on. It's all kind of wrapped up. It's 4:45 now. In the session on Friday, we'll work through some of the exercises. Okay. They're not SAGE exercises. This is one area maybe dealing with these kind of things where SAGE isn't so useful or fully featured or that.